periodic table. We are referring to columns 13 through 18 on the right-hand side of the table. Elements in the p block have their outermost or valence electrons in a p orbital, B2H6, whose structure is illustrated here, is another important compound of boron. Boranes are a class of compounds containing only boron and hydrogen. Diborane is a colorless, highly toxic and extremely reactive. This colorless and highly toxic gas has a boiling point of 180 Kelvin. There are several ways to prepare diborane. One route involves reacting boron trifluoride with lithium aluminium hydride in presence of diethyl ether, as shown by this chemical equation. In the laboratory, oxidization of sodium borohydride with iodine produces diborane. Sodium iodide and hydrogen gas are the byproducts of this reaction. Try to answer this question on your own before continuing. Identify the oxidizing agent and the reducing agent in the reaction of sodium borohydride boric acid, fuels for rockets, because of their exothermic reaction with oxygen. When placed in water, diborane undergoes hydrolysis to form orthoboric acid, as shown in the reaction here. Hydrogen gas is also released in this reaction. Diborane undergoes cleavage reactions with Lewis bases. In these reactions, the diborane molecule breaks apart to form borane adducts with the Lewis base. Two examples of these cleavage reactions are shown. One with trimethylamine and the other with carbon monoxide. Diborane can react with ammonia. Initially, the reaction of diborane with ammonia produces an adduct diammoniate of diborane. This exists in a slightly different form, as shown in the chemical equation. When this substance is heated further, borazine, B3N3H6, is formed. Note the alternating boron and nitrogen atoms in the six-membered ring of borazine. Since it resembles structurally with benzene, it is called as inorganic benzene. Diborane is an electron-deficient molecule. Notice the peculiar structure of it. The two boron atoms and the four terminal hydrogen atoms of the molecule are all in the same plane. These four terminal BH bonds are regular two-centered two-electron bonds. The bridging hydrogen atoms lie above and below this plane. The two bridge BHB bonds are unusual three-centered two-electron bonds. The bond lengths are different as well. The bond length of the bridging hydrogen and boron is 134 picometers in length, while the bond length of the terminal hydrogens and boron is only 119 picometers. The boron atoms in diborane undergo sp3 hybridization. The overlapping of a vacant sp3 hybrid orbital of one boron atom and sp3 hybrid orbital of another boron atom containing one electron with the pure s orbital of bridging hydrogens containing one electron results in the banana bonds. Similarly, other banana bond is formed on other side. Thus, the two banana bonds formed lie above and below the plane of the boron atoms. The remaining two sp3 hybrid orbitals of each boron atom overlap with terminal hydrogen atoms to form normal sigma bonds. This results in the formation of 4 terminal hydrogen bonds. Boron forms a series of hybridoborates. One such ion is the borohydride ion, BH4-, which has a tetrahedral geometry. Sodium borohydride and lithium borohydride can be prepared by reacting the metal hydride with diborane, as shown in the equation here. Borohydrides are good reducing agents. Thus, they are widely used in organic synthesis, as well as to prepare other metal borohydrides. Boron has a number of applications. Because it is a hard solid with a high melting point, low density, and low electrical conductivity. Boron fibers are used to make bulletproof vests and light-weighted composite material for aeroplanes. The boron-10 isotope has a high ability to absorb neutrons. Therefore, metal borides are used as control rods and protective shields in nuclear power plants. Borax and boric acid are used in the manufacture of heat-resistant amorphous forms. There are 3 important crystalline allotropic forms of carbon: diamond, graphite, and fullerenes. Diamond, the first allotrope of carbon, is the hardest substance on Earth. Diamond has a crystalline lattice in which the carbon atoms are arranged in a rigid 3-dimensional network. In diamond, all carbon atoms exhibit sp3 hybridization. Each carbon is bonded to 4 other carbon atoms situated tetrahedrally around it. The C-C bond length is 154 picometers. This directional network extends in space and produces a 3-dimensional network of carbon atoms as shown in the illustration. Try to answer this question yourself before proceeding. The carbon atoms in diamond are covalently bonded. Why is the melting point of diamond very high? Recall that each carbon in diamond is attached to 4 other carbon atoms surrounding it. It is very difficult to break up this covalent network as it is very rigid, and hence diamond melts at an extremely high temperature. Since there are no free electrons in a diamond crystal, it is a bad conductor of electricity. Another important allotrope of carbon is graphite. You are probably the most familiar with this form of carbon for its use in pencils. Despite the name, pencil leads are actually made of graphite. Graphite has a layered structure. These layers are held together by the weak van der Waals forces of attraction. The distance between any 2 successive layers is 340 picometers. Each layer of graphite is made from planar, hexagonal rings of carbon atoms, as shown in the diagram. All the carbon-carbon bonds are 141.5 picometers in length. Each carbon in graphite is sp2 hybridized. Each atom forms 3 sigma bonds with its 3 neighboring carbon atoms. The 4th electron of each carbon is involved in pi bonding. Using the unhybridized p orbital on each carbon atom, as shown in the illustration. The electrons involved in the pi bonding are delocalized. This means that they are free to move, and thus graphite is a good conductor of electricity. Try to answer this question on your own before proceeding. Why is graphite soft and slippery? The layers in graphite are held together by the weak van der Waals forces of attraction. Thus, the layers slide past over each other and break off easily. When you take notes with your pencil, you leave layers of graphite behind on the paper. The third important allotrope of carbon, the fullerenes, are the most recently discovered. They were identified by Robert Kerr, Harold Kroto, and Richard Smalley in 1985, for which they were awarded the 1996 Nobel Prize in Chemistry. Fullerenes can be prepared by heating graphite in an electric arc in the presence of inert gases. This work led to the discovery of the two most important fullerenes. Molecules containing 60 and 70 carbon atoms, respectively, plus traces of other fullerenes. Fullerenes are cage-like molecules. C60, or Buckminster fullerene, named after the American architect famous for his geodesic dome structures, looks like a soccer ball. It is sometimes referred to as a buckyball. Buckminster fullerene contains 60 carbon atoms arranged as a hollow sphere. This ball-shaped molecule has 60 vertices, each occupied by a carbon. It contains 20 6-membered rings and 12 5-membered rings. A 5-membered ring is fused with only 6-membered rings, while a 6-membered ring is fused with 6 or 5-membered rings. All the carbons in the Buckminster fullerene molecule are sp2 hybridized. Each carbon atom forms 3 sigma bonds with its 3 neighboring atoms. The remaining electron in each unhybridized p orbital of carbon is delocalized in molecular orbitals, giving the aromatic character to the molecule. Two different bond lengths are observed in Buckminster fullerene. The carbon-carbon single and double bond lengths, as observed in C60, are 145.3 and 138.3 picometers, respectively. Each carbon atom forms formally 2 carbon-carbon single bonds and 1 carbon-carbon double bond. Under standard conditions, graphite is the thermodynamically most stable allotrope of carbon. Since it is considered as the standard state of carbon, its heat of formation is set at 0. Both diamond and fullerenes have higher heats of formation, reflecting their lower stability. The heat of formation of diamond is 1.90 kJ per mole, and the heat of formation for fullerene is 38.1 kJ per mole. The amorphous forms of carbon include carbon black, coke, and charcoal. Carbon black is formed by burning hydrocarbons in a limited supply of air, or by incomplete combustion. It is an almost pure form of amorphous carbon containing 98 to 99% carbon. Coke is formed when wood is heated at high temperatures in the absence of air, which is called the destructive distillation of wood. To form charcoal, coal is heated at high temperatures in the absence of air. Carbon has a wide variety of uses in its elemental forms. Diamond is widely valued in jewelry. They are measured in carats. 1 carat is equal to 200 milligrams. Diamond, both natural and synthetic, is used as an abrasive in sharpening tools, die making, and in the manufacture of tungsten filaments for light bulbs. Graphite is used as a dry lubricant in machines running at high temperature where oil cannot be used. Graphite is also used to make strong and lightweight composite material for tennis rackets, fishing rods, aircraft, and canoes. Carbon monoxide is a colorless, odorless gas that is nearly insoluble in water. The carbon monoxide molecule contains 1 sigma bond and 2 pi bonds, as shown in the illustration. There are several ways to prepare carbon monoxide. The first way is the direct oxidation of carbon in a limited supply of oxygen or air. The reaction shown here is an example of incomplete combustion. Another way to prepare carbon monoxide is the dehydration of formic acid, also known as methanoic acid, with concentrated sulfuric acid at 373 Kelvin. On a commercial scale, carbon monoxide is prepared by passing steam This reaction produces carbon monoxide and hydrogen. This mixture of carbon monoxide and hydrogen is called water gas or synthesis gas. If air is passed over hot coke, nitrogen is produced along with carbon monoxide. The resulting mixture of carbon monoxide and nitrogen is called producer gas. Water gas and producer gas are important industrial fuels. The carbon monoxide in these mixtures can undergo further combustion. This produces carbon dioxide and liberates a great amount of heat. Carbon monoxide is a powerful reducing agent. When exposed to metal ores, it reduces most of them to the elemental form of the metal. Note that carbon monoxide cannot reduce the alkali and alkaline earth metal oxides, aluminium oxides, and the oxides of certain transition metals. Reactions with carbon monoxide are used to extract many metals from their ores. The reactions here show iron 3 oxide and zinc oxide producing iron and zinc. In the process, carbon monoxide is oxidized to form carbon dioxide. Since the carbon in CO has a lone pair, it can act as an electron pair donor. Therefore, carbon monoxide can react with certain metals when heated to form metal carbonyls. Several types of metal carbonyls are illustrated here. It binds to the Hem group of hemoglobin 300 times more strongly than oxygen. The hemoglobin molecule is, thus, prevented from transporting oxygen. This can ultimately lead to death if not treated promptly. Home carbon monoxide detectors are available and can be life-saving. Now let's turn our attention to carbon dioxide. These organosilicon polymers have a monomeric unit of R2SiO, where R is an alkyl group that repeats many times. Let's see how silicones are manufactured. First, methyl chloride, CH3Cl, is reacted with silicone in the presence of a copper catalyst to form methylated silicones. In addition to the dimethyl dichlorosilane shown here, trimethylchlorosilane and tetramethylsilanes may also be produced in small amounts. Next, the dimethyl dichlorosilane is hydrolyzed, as shown in the reaction. Finally, the straight-chain polymer is formed by condensation reactions. To control the length of the polymer, adding trimethylchlorosilane blocks ends the chains. Silicones are water-repelling in nature due to the repetition of non-polar alkyl groups along the chain. This makes them useful for waterproofing fabrics. Silicones generally have high thermal stabilities, meaning that they are stable in high temperatures. They have high dielectric strength, which means that they can withstand high electric fields without breaking down. They are essentially inert chemically. They are resistant to oxidation and to most chemicals. These properties of silicones make them very useful. Silicones are used as sealants, greases, and electrical insulators, as well as for waterproofing fabrics. They are also used for surgical and cosmetic implants, as they are biocompatible. Silicates are another